Good morning, everybody. We've got, roll sheet. So I'll start this at this end this time. We'll see where it ends up to try to get it to snake along the rows. And when it gets to the back, send it back to the front so if it misses people. And we'll stop doing that next week. Let's see. Chapter, so today and Thursday is chapter 20. So kind of a big chapter, there's lots to do. And then, that's kind of the theme, isn't it? At the end of every unit, it's like the biggest chapter of the unit. And then, let's see. Next Monday, we do the voltage / electric field lab where you're going to be drawing pictures. So I need you next week, I'll keep reminding you, have like minimum a pencil and a pen. To be thinking, but like even better, different colored pens, crayons if you would like, colored pencils. We just need two different like colors or mediums to draw in, and that'll make sense when we actually do the lab. There will be a tiny bit of math in that lab, but not much. And then next Tuesday, it's electric field mapping, yeah. Next Tuesday, what are we doing? We are reviewing for the exam that happens a week from this Thursday. Right, so next week is your first exam, Unit 1. We'll spend some more time on that Tuesday, sort of orienting you to the exam if you're new to my class. Those of you in Mr. Evans' class, he was very worried about you the other day. He asked how you were doing, and I just gave him a fantastic report and told him that you don't like my jokes as much as his. Let's see. Yeah, so that's kind of like the next 2 weeks in a nutshell, right? Coming up on cram. Are you taking exams yet in your other classes? No. Not quite yet. Chemistry this week? Next week? Yeah, so all the teachers, we get together and we schedule all the exams on exactly the same days. We sit there, we go, let's see, Jack, how could we stress Jack out the most?
Everything the same.
Just everything the same way. No, it's naturally, it just happens that way. Okay, we are gonna, I was gonna say we were gonna dive into circuits, so we've got a little bit more to take care of before we get to like kind of building circuits out and figuring out where all this charge is going. And we really need to talk about a couple of ideas here. Let's tackle, we'll do Ohm's law first, and then we'll talk about resistance. So it really is, this is one of the foundational, like this controls your life in more ways than you can possibly imagine. But it's not something that you will use very often in a practical sense. Like a normal person can go through life without ever knowing Ohm's law. You guys, of course, will get tested on it. But like, this is like the key like idea in all of circuit theory. So what Ohm's law tries to do is it tries to figure out what the relationship is between current and voltage. And current being the flow of charge, voltage being the pressure or push that charges will experience in a circuit. What's your guess? Directly proportional or inversely proportional to each other? Inversely, so the more voltage, the less current? Yeah, it's the other way around. It seems like it should be the other way around, right? Bigger number, bigger current, right? Bigger voltage, bigger current. Push harder, get more charge to flow. That's exactly what it is, right? But again, we can't just put an equal sign here, right? Because they're not the same thing, right? I mean, even the units are just wrong. So we need a constant, right? And write down the thing in the box when I'm done. So normally we would stick the constant sort of after the equal sign. It's always constant, then like variable or whatever. We're actually going to flip this around, okay? So technically like that, but that's not how we write Ohm's law. Instead, we write Ohm's law like this, okay? Where the constant of proportionality is that big R. And you want to take a big guess as to what it stands for? Resistance. Okay, so it seems kind of weird that resistance would be this constant of proportionality between voltage and current, and it is. But there's there's a reason it's called resistance. What do you think it does in a circuit? Resists what? Current, right? Like it resists current flow. We're going to use several analogies here, and I want to prime your brain for them before we get into the videos. Batteries provide voltage, which are like pumps. They provide energy to charges. Current is a way of measuring how much charge is going somewhere. And then resistance tells us how much energy the charges are giving up to do work. So if batteries are like pumps, resistors are like waterfalls. So batteries will boost charges' energy, they'll lift them up, those charges will flow around, and then they will be used up by something, a device like a light bulb or a refrigerator or your phone or whatever. Like resistance becomes this catch-all idea for anything that uses electrical energy. It resists the flow of charge, and in doing so, causes a lot of things to happen, mostly work, but we'll talk about heat and some other things. Okay, what are the units of volts? Volts. It's kind of a weird question. What are the units of current? Amps, right? And so what are the units of resistance? Meditate on it. Ohm. George Frederick Ohm. We use the symbol Greek capital omega, the last letter in the Greek alphabet. And technically, I guess an ohm, right, is a volt per amp, if you kind of want to do that. In 2B, you're going to learn that you really don't want to chase units around too often because you're going to go crazy if you do. There is a certain sort of madness that will ensue if you really try to go down the rabbit hole too far. This is why I always teach standard in equals standard out, right? You're guaranteed to get an ohm as long as you put your current in amps. So if the problem gives you milliamps, what are you going to do? You're going to make sure it's times 10 to the 3, or negative 3, right? Like so that's what you do, right? Same thing with the voltage, all that kind of stuff. Put it in a standard unit, and then if you're solving for resistance, boom, you're going to get it. I am not sorry for what is about to transpire. What's this? That's the letter omega, but it is an ohm, right? It's the symbol we use for electricity, right? Okay. What's that? An ohm. No, that's an ohm away from ohm. That wasn't very good. That was good. Okay, fine.
I thought you were going to say that, like, oh, technically that's a lowercase.
Yeah, no, it's an ohm away from ohm. This is an ohm, right? What's that? Pac-Man. No, it's an ohm meter. An ohm eater. Ohm meter. It's getting better. Okay. Okay, so this one takes a little bit. Ohm on the range. You're welcome.
It got progressively better.
Did it? Okay. Got to make sure I preserve that order then. Okay. Now, the other thing about resistance, okay, is it has like physical dependencies. The resistance in a wire will depend on the material that the wire is made out of. Like, so the resistance in like a copper wire is different than the resistance in an aluminum wire. An actual resistor, a circuit element that does nothing except like impede the flow of charge, They can be made out of ceramics. They can be made out of carbon. Like the amount of resistance that something has depends on some physical parameters. And those parameters are resistivity. That is not density, even though it's the same Greek letter. Okay, context is everything, right? That rho right there is a resistivity. That's the material type, right? So carbon has a different resistivity than, say, plastic, than, say, copper or gold, right? They all have different resistivities associated with them. The length that the resistor has, so like if we're talking about a wire, and I know it's kind of funny to talk about like conducting wires that have resistance, but everything has resistance, just a question of how much, right? Divided by the cross-sectional area. So what do you need to do with a wire to reduce its resistance? Let's think about like transmission wires, right? Getting electricity to our homes, right? Do you think you want the resistance to be really big or really small?
Really small.
Why? Why small? More power, electrical energy can be delivered to our homes, right? Because what resistance does in wires is it steals energy away. It converts electrical energy into thermal energy. And so that energy can't be used. You heat up the wires, you can't use that to heat up your home.
Practically speaking, does that mean it costs more money?
Yes, and well, because PG&E will just pass the losses on to us, right, as the customer. So there's a charge on your bill called the transmission charge, right? There's production, making it, and then there's transmission, getting it to you, right? You get charged for both. So if we can lower the resistance, then that would be good. So what do we do to lower resistance? Oh, okay. So if we make the cross-sectional area of the wire bigger, that's what that A is down in the denominator, right? If we grow that wire out, right, the resistance goes down, doesn't it? Bigger denominator, smaller resistance. Or a shorter length, right? So should we just park the nuclear reactors directly in your backyard?
Well, the government doesn't
You can
like
swim
it when
in
we
it.
do that.
That's my preference, actually. Given the choice of what kind of power plant to put in my backyard, if it can't be a renewable, nuclear is my first choice, right? Definitely better than coal, definitely better than oil, definitely better than natural gas. So we'll get to the nuclear power plants at the end of the course. But yeah, okay, so rho you really can't, okay, fine, right? We'll just make all the wires out of gold, right? It's got a lower resistance. No. Expensive, gold breaks really fast, right? There's a lot of other considerations here. So rho you really can't do much with. And length is kind of, you just got to get it to the houses, right? Okay? A lot of our electricity here in the Central Valley comes from hydroelectric power that's up here in the mountains. Another large portion of our power in the Central Valley comes from natural gas plants in the Bay Area. We get a little tiny fraction of it from the nuclear power plant over near Morro Bay, and it varies. Okay, what's that?
Power plant.
No, got retrofitted. And then more and more, California's electrical power is coming from renewables, solar, wind. So we get from like Tehachapi, the windmills that are over there, in the Mojave Desert, and some of the solar stations in the Mojave. So I believe it was 2024. It was the last time I looked up the statistics. There was I think it was like almost 100-day period where over the summer months, California ran on 100% renewable power. Yeah, no, it's fantastic, right? Like that's like win because not only did it demonstrated during one of the hardest times for our electrical grid, which is in the summertime, okay, but they managed to use renewables in such a way that even overnight there was generation from battery storage facilities and all that kind of stuff. So this is not, it's been, Britain's been doing this for like the last 5 years, right? Like I think Britain is almost to the point where they've got the whole year on renewables. Yeah, like it's crazy. But they have the North Sea and a bunch of windmills up there. So this is happening, right? Notwithstanding the administration's attempts to make it not happen, it's been happening for a while. So we can't do much about the length. We can play with the cross-sectional area. We can make the wires bigger, but again, you get the weight of the wire and you get the cost of the material. So there's always some optimization that's going on here, but we can mess with the resistance in that way. Okay, let's watch some videos. Just try to bring home ideas about resistance. And nope, this one. About resistance and what's going on. So in these videos, look for like the ideas or concepts that they're trying to portray. Like in this video, you're going to see a battery connected to a resistor, and the battery is going to look like steps going up, and the resistor is going to look like steps going down. They'll show the charges kind of flowing around there. Just giving you some analogies to play with.
To make a current flow through a conducting material, a voltage is needed.
See how the battery steps
Current
up,
is always proportional
current
to
goes
the
down.
voltage. The constant of proportionality is called the resistance. This equation is known as Ohm's law. An element in an electric circuit with resistance is called a resistor.
And so if we made the resistor bigger, right, if those steps got steeper, then we would need more battery, right, to try and push that energy up. I just noticed, not only do I have the windows open, but somebody turned all the lights on. Who puts a light right in front of a screen? I mean, just give me a second. I gotta. Nope. Okay, so that's not zone 1. Aha! Zone 4. Did that help at all? Yes. A little bit. Okay. So I'll just feel like I'm up here in the dark. That's okay. I'm always in the dark. We had that one. Okay, so let's take a look at this.
Under the influence of an electric field, electrons move through a metal much as a marble falls through a viscous fluid. If it weren't for resistance, they would accelerate freely, like a falling body in a vacuum. But as it is, they move on the average at a constant speed. Resistivity is like viscosity. The more of it a material has, the slower a particle will move through it.
So which of these has more resistance? The one on the left, the yellow one, right? Okay. And so it's like most, middle, and this kind of one, it kind of went through fast, right? So resistance can be thought of like viscosity or like the thickness of a fluid. It's friction in the electrical sense, right? The more friction you have, the slower something's going to get going. Thank you very much. And all that kind of stuff. So again, just trying to give you some analogies and pictures and that kind of stuff.
Have you ever seen your house lights dim when you turn on a heater or heavy appliance? We'll use this model of house wiring to demonstrate the effect. 2 resistance wires will substitute for the normal copper wires used in a house to increase the effect. They run ordinary household current into this bank of lamps and heaters, which can be switched on and off individually. We'll first switch on the lamps. Then heaters will be switched on one at a time. When enough heaters are added to the line, the lamps dim. The electrical energy lost in the wires which deliver the current is dissipated as heat.
Okay. Yeah, how important is it to have the correct wires in your house? Pretty important, right? If you've ever blown a circuit in your house, right? tried to run too many things at the same time and it like trips the circuit breaker kind of thing. Those are safety systems in your house wiring that are designed to prevent exactly what we just saw. Okay?
Is that when you see houses that like basically disintegrate? Is because all the like wires just like burn?
That's just because fire. Okay? The question is, what was the ignition source? Right?
I don't understand why the wire, we had 3 wires, right? And then it
Two,
looked like,
yeah.
2 wires, then it looked like
Fire.
1 wire.
Mm-hmm.
Was it just too much going
Yeah,
on at once?
yeah. That setup, okay, did not have any safety features in it. And in fact, they said that they replaced the normal wire with something called resistance wire. It's designed to kind of heat up and melt as it gets more and more resistant. And so assuming that like the circuit breakers didn't work in your house, right? If you tried to turn on the microwave, the coffee maker, the hair dryer, and the vacuum cleaner all on the same circuit, which shouldn't be able to happen at your house because they should all be separate, right? Then you would be drawing so much current through that wire, and the resistance of that wire is what it is. With all of that current, the resistance is just going to start taking that current and turning it into heat. And what do you need for fire to happen? You need fuel, you need oxygen, and you need heat. Okay? So the wire is going to provide plenty of the heat if it's not up to code correctly and all that. Now it doesn't guarantee, circuit breaker doesn't guarantee you won't have an electrical fire. If a rat gets into your wall and decides to chew on an electrical wire, right, and short circuit that wire and that causes a spark, right, the safety system might shut off, right, but if that spark happened and it happened near something flammable, then there's going to be a fire. So these are all considerations, right, when it comes to thinking about resistance and its practical applications. All right, so let's do a quiz. Get your quiz sheets out.
I'm not doing any like A divided by 2.
No. It's just the total. The total is. I forgot about this. We have okay. So. Aha! Here it is. Try not to ask questions.
We'll skewer this hot dog onto 2 nails and run a current through it to show the heating produced by the current.
Because why not?
110 volts are applied to the nails, and a current begins to flow through the hot dog. After a few minutes, the hot dog begins to steam from the heat produced by the current.
So wait, are hot dogs conductors?
Yeah.
Apparently, right? Because otherwise that circuit, right? Hot dogs are not insulators. They're conductors mostly because they just have a lot of salt water in them, right? So the ions can flow freely. So where did the heat come from? The resistance, right? That was inherent in the hot dog. I'm thinking science club fundraiser. We just set up a bunch of live electricity out near the fountain, plug in some hot dogs, provide some mustard.
Signs or warnings.
No, we got the fountain right there too. We can just put the.
It'll be fine.
It'll all be good, okay? And if you're gonna do a hot dog, why not do a pickle?
We'll use this pickle and 2 nails to show an unusual type of electrical discharge.
It's gonna be better or worse.
The nails are inserted in the ends of the pickle, and electrical
assuming
leads
maybe-
are connected to the nails. When we put a high voltage across the nails, the pickle lights up at one end.
Is that the negatively charged side?
Yeah, okay, we need a chemist is what we need, right? Yeah, because here, so pickles, mostly salt water too, okay? Pickles, hot dogs, same thing,
Yeah.
to within a general approximation. So the thing with the pickle lighting up in the end, I've been told by chemists, has to do with like sodium ions. and the sodium being electrified, vaporized. It's kind of the same thing that you would like a sodium lamp kind of thing, or doing spectroscopy on sodium, right? Burning sodium in a flame, that kind of stuff. It's just that the resistance, the heating of the end of that pickle, and it's always the whatever end it is, I don't know if it's positive or negative, right? Is always where those ions are gathering, and so they light up and all that kind of stuff. So anyway, I will not be held responsible if you go home and plug pickles into the wall.
Don't do it. Your modern kitchen won't like you.
Yeah, well, well, I was going to say fun, but that fun is spelled with P-H-U-N. Okay. Before we get to circuits, we're going to take a slight little tangent and try to make this practical. Okay? I've been hinting at this. We've been dancing around the subject of like what's going on in your house, but let's talk about PG&E. Okay? Electrical power. Does anybody remember what power was from 2A? Don't panic if you don't remember, but does anybody remember?
Watts per...
The units were watts, right? And it was work divided by time. But since energy was the same unit, remember work and energy are both joules, right? That's kind of the equivalence, right? And the units were watts. And what was a watt? It was a joule per second, okay? Back in my class in 2A, like, I think I remember asking something along the lines of, well, where have you heard of watts before? And everybody's like, well, the light bulbs, right? Okay? Or the charger on my phone or something. Like, do I have a 10-watt charger? Do I have a 40-watt charger, right? So that unit watts is usually associated in general everyday society with some sort of electricity measurement, right? But so we have volts. We know about volts, right? We know about current in amps. Now we know about resistance in ohms. Power, electrical power, in your book, I didn't write it down, so I'm going to make it up. Power is going to be equal to current times voltage. So again, what are the units of current? Amps. What are the units of volts? Volts. So an amp times a volt is a watt? Yes. An amp times a volt is a joule per second. Like I said, don't go down the rabbit hole. Just don't. Okay? So there's sort of the electrical version, right? It's not that this version over here is wrong. It's not, right? It's just that we can cut straight to our key ideas of current and voltage in the context of power. But the power here, again, is going to be in unit of watts, which is a joule per second, which is an amp times a volt, right? Okay, because we have Ohm's law, we can kind of do power in a couple more ways. This is all the same equation, but I could substitute in for that V, IR, and then what do we get?
So
I squared R, right? That's another, so like if you don't know the voltage, right, but you do know the current and resistance, kind of a shortcut for getting to the power, right? This one right here has an interesting, not side effect, but it gets its own name because this is often referred to as the power lost equation, especially when it comes to electrical transmission lines. The amount of power that is consumed simply by the resistance of your device, simply by the resistance of the wire, goes as the square of the current. So if you're PG&E and you want to lose the least amount of power in getting it from the dams to the homes, right? What do you want to make as small as possible? The current, okay? because the power lost equation tells you how much power the electrical resistance in the electrical conductors is going to cost. Okay? So PG&E goes out of its way to make the current as small as possible. We are not yet to the level of sophistication we need to explain how to do that magic of how do you lower current and still be able to transmit energy. We will get there after we learn about magnetic fields, okay? Because this is where AC is really important for transmitting electrical power, but DC is needed for running devices and computers and things like that. So we need to learn about AC before we can delve into this more. But when we get there, I'll mention this equation again, right? I'll say the power lost by electrical lines goes as the square of the current. This is what we're talking about right here. Okay, what's the other version that we can get of this? We kind of, if we manipulate this current right here, we solve for the current, we get V over R, and then we shove that up in there, what happens?
V squared over R.
Yeah, we get V squared divided by R, okay? All of those in the boxes are giving you the same number. It's just simply a question of what you know, right? What are you given? What do you know? What are you solving for? Use the one that is appropriate at the time. Try not to, again, here's another rabbit hole you don't want to think about. Is power directly or inversely proportional to resistance?
I don't know. Both.
It depends is the answer, right? So try not to think of power and resistance as being like going together, right? They can either be directly or inversely depending, right? So don't think of it that way. Think about it in terms of current and voltage, right? What's going on with the power in terms of current and voltage. So, but generally power loss, if we had to default to an answer, we'd say power goes up with resistance, right? They're like directly related to each other, which is why that power lost equation kind of comes into play, especially when we start talking about electrical energy distribution. Okay, I think I told you everything about that. But here's a question. So this is your practical application for like this entire class. What do you pay for to PG&E or SoCal Edison, whoever your electric provider is? What do you pay for on your bill? It's a kilowatt hour. Okay? What the heck is a kilowatt hour? Be careful. It is not a kilowatt per hour. Okay? It's a kilowatt hour, which means a kilowatt times an hour. Jack's face is the perfect one. Okay? This was his face. What's a watt?
A joule per second.
It's a unit of power, right? Okay? And if we get really kind of down to it, okay, it's a joule per second, right? Or let's make even more generic here, right? Okay? It's an energy per time times a time. So what is a kilowatt hour? It's a unit of energy. It's just kind of a weird unit. It's not even really a stupid unit system unit, because hours are used in the SI system, right? It's not the standard, because seconds would be the standard, right? But watts is very definitely an SI unit, okay? So does anybody know what the unit of power is in the stupid unit system? Horsepower. So yeah, PG&E is going to provide horsepower seconds.
Why not just give us energy? Why give us kilowatt per hour? Is there a standard for energy?
This is the standard for electrical energy distribution and consumption.
It's just semantics.
Yeah. So Pete, you would freak out if you saw the number of joules that you were consuming at your house. Okay? This is similar to the dietary calorie and the actual calorie. When that soda says 150 calories on the can, right? That's really 150,000 calories, right? They're shoving some zeros off, right? They're kind of doing something similar here. And it's not because there's no conspiracy here, okay? Engineers get tired of carrying too many zeros around. It's really easy to make a mistake when you've got a lot of zeros on a number, right? So if you can come up with a unit that allows you to capture what's going on, but not have to keep like 6 zeros that are never changing, right? Do it that way. Really, it leaves less room for error.
So on a practical level, right, it'd be like if you had an appliance that drew 1,000 watts.
Yep.
You ran it for exactly
for an hour. So this is basically what your air conditioner does, okay? So if your air conditioners usually run, it depends on the air conditioner, but let's just pretend that it is a 2,000 watt air conditioning unit. Some run as high as 6 or 7, others like down to 1.5. It's always over 1,000 watts, right? So if it's a 2,000 watt unit, how many kilowatts is that? 2. It's 2. Do you see what they did there? They got rid of some zeros, right? So you say it's a 2 kilowatt unit, right? How long would you have to run a 2 kilowatt unit in order to have 1 kilowatt hours worth of energy?
An hour?
No.
A second?
No.
A minute?
Do you want to keep guessing? It's 30 minutes.
That's what I said.
Okay? So it's 2 kilowatts times half an hour, right? Would give you 1 kilowatt hour. 1 kilowatt unit would have to run for an hour to consume the same amount of energy. Okay? So that's kind of what's going on here, right? So bottom line, your 40 watt phone charger versus your 10 watt phone charger. Which one consumes more energy in the same 10-minute period of time? The 40 watt, right? Bigger number, more energy consumption, right? Does your phone charge faster? Yes. Assuming your phone can take all 40 watts, right? You're giving it more energy in the same amount of time than if you would, say, with a 5 watt charger. Okay? So this energy consumption unit is kind of handy. It can be a little bit strange to think about. So an old-fashioned incandescent light bulb would run on about 100 watts, right? So if you ran 10 100 watt light bulbs for an hour, 10, and how would I write 100 watts in kilowatts?
0.1.
It's 0.1 kilowatts. That's a 100 watt light bulb, right? For 1 hour, what's this answer? It's a 1 kilowatt hours worth of energy, right? So a standard home has way more than 10 light bulbs in it, right? And so if you turn on all the lights in the house, right, for an hour, you can use it. Now, go and replace all those light bulbs with LEDs. And we're just going to round. LEDs are more efficient than this, but we're just going to round to 10 watts. Okay? A 100 watt equivalent in terms of the amount of lumens that come out is about 7.5 to 9 watts, depending on the manufacturer. But let's just round to 10 watts to make the math easier. Okay? How many light bulbs running at 10 watts? Let's do it the other way around. Yeah, how long could you run 10 LED bulbs at 10 watts compared to an incandescent bulb? 10 times as long, right? So if a house that had 10 light bulbs in it switched to LED bulbs, roughly you can run those light bulbs 10 times longer for the same amount of energy. And now we're talking about efficiency, right? Okay? It's because the power per bulb is lower, and so you can run it longer to get the same amount of energy consumed. That's the game you're playing, okay, when it comes to electrical power. This is a very old bill, okay? So the costs are not going to be right. This comes from my house, Okay, I just want to point some things out that PG&E changes this every year or two. This is the conspiracy theory. They obfuscate, which is a fancy word for they want to hide key pieces of information that they are legally required to tell you. Okay, but let's take a look at some of this stuff. Baseline quantity. Notice they gave me a number, and for some reason put a lot of zeros on it. What's that unit?
Kilowatt hour.
What are they charging me for?
A kilowatt per hour.
Energy. Is PG&E a power company or an energy company? They are an energy company, right? And they do everything in units of energy here, right? What's the baseline?
So like it's tiered to where like you probably like the first portion of it is a certain price, and then after a certain point, then you start.
Were you aware that there's a maximum amount of energy you're allowed to use at your house every month?
No.
Yeah, it's called the baseline.
There's also time.
Okay, so well, that gets even more complicated. But there's a baseline quantity that is decided in a collaboration between the government of the state of California and PG&E / SoCal Edison. Okay, this baseline quantity represents the amount of electrical power that you are allowed to use at your dwelling place, business, whatever, right? Based on a lot of different things like time of year, like what month it is. Anyway, a bunch of things, okay? Now, is PG&E going to turn off the power as soon as you use, in my case, 307.5 kilowatt hours? No. Like if I'm on day 20 and I get to that number, are they just too bad? You got 10 days, you're going to be in the dark? No.
How do they charge you a fraction of a cent?
Don't think about this too much, okay? What happens when you go over the baseline? The amount that you are allotted, they charge you more. So this is where you get a tiered pricing strategy, okay? And this is what happens in the state of California, okay? You get a baseline, and then you get these, like if you exceed the baseline by 30%, okay? Notice they changed the price that they're charging, right? It was about 12 cents per kilowatt hour, and it went up to 13, okay? And then basically if you go from 30% to 100% more, right? See how they basically doubled the price per kilowatt hour? This has changed over the years. It changes with legislation. It changes with whether or not PG&E is starting wildfires. It changes for a lot of things, okay? Currently, the system is I think it's a 3-tiered system, and there's something called time of use, where the amount that you are charged per kilowatt hour depends on the time of day during the summer, not usually during the winter. It gets complicated. There is a website that will show you in real time what the price per kilowatt hour is like on the California market. In fact, every 5 minutes there's an auction that takes place. And this auction is computer controlled, okay? Because PG&E and SoCal Edison and other power grids interconnect, like with the state of Nevada and Oregon and Arizona, Mexico. We interconnect, okay? Baja, those areas, right? We interconnect with them. And so let's say that Nevada generates more than it needs in a 5-minute period, right? They can sell some of that energy to California and vice versa, right? So there's this fluctuation that takes place every 5 minutes depending on demand and supply and all these different kinds of things. So that's taken into account for the amount. It's very complicated now, okay? But how do you as the consumer work this system? Did you have a question?
Oh, I was gonna say, so you mean like every 5 minutes those prices are like?
Will adjust.
Wow.
It adjusts for PG&E and all the power companies, and then they kind of they charge an average. So the time of use, like the factor, the extra they're charging you. So like if you use your air conditioner in the heat in the middle of the day, you're getting charged more for that electricity than say using it at night when there's less demand.
Is that why my dad asked me to use the dryer at night?
Yes. Okay. So.
I thought it was the opposite. It's like everyone's home during the like 5 to like 12, so then that's the more expensive.
5 p.m. to 12 p.m.?
Yeah.
Yes. Yeah. It's like 9 p.m. is sort of when it starts sort of falling off again and that kind of stuff. So how do you deal with this? If you are directly responsible for paying for the electricity that you use, right? And you want to play the game of minimizing that cost, right? What do you do as a consumer?
Use everything in the middle of night.
Automation.
Live off grid.
Live off grid. Okay. So yeah, I'm guessing as a student you probably don't have the capital to put solar panels on your dwelling, right? Or permission to do so, right? If you don't own your house, that kind of thing, right? So all of those things out, you got to pay the man, right? So how do you reduce or control your energy usage to have the least amount of pay? Less resistance in your appliances. Getting more efficient with the power usage, right? Because an LED light will consume a lot less energy in the same amount of time. And you're like, yeah, but it costs a little bit, it costs more to buy it. It's going to save, itself over time. But so you need to reduce your energy usage if you want to save money. Because when you are in those lower tiers, like tier 1, that's where the least charge is happening, right? If you're consuming a lot of electricity, you're getting bumped into those upper tiers, then you're just paying a lot of money for that electricity. Okay? So you want to try and get down in your tier. So look at your bill. See what tier you're sort of following in for a given month, right? And PG&E will let you go back and look at previous months to see how much you used and what tier you were sort of in over time, right? And if you can find ways to lower that, like if you have an electric dryer, running it in the early morning or very late at night, right? When you're being charged less for electricity at that point, okay? Getting a heat pump dryer, which again are expensive, but are more efficient and all that kind of stuff. If you are in a situation where you are supporting yourself, limited income, all that kind of stuff, call PG&E. They have programs for students and low-income families, right, to charge you a different amount of money based on your circumstances, right? And a lot of people don't realize that those programs exist. My wife and I have medical devices that we need to use every night for our sleep apnea. And so we called up PG&E and we said, is there anything you can do for us? And they said, yes, we have a program called Medical Baseline, right? They made our baseline number bigger because we have to run these devices all night long for medical purposes. And so they knew that there would be like this constant amount every night. I think between the two machines, it's about 300 watts, right, of just constant for 8 hours at night. So they just adjusted our baseline usage to recognize that, right, so that we don't have to pay extra just to have our medical equipment going. So there's lots of sort of ways to do this. But fundamentally, the best way is just to listen to your parents. And if I can be non-politically correct for just a second, listen to your father. What was your father constantly yelling at you to do?
Turn off the lights.
Why?
Watch the AC.
Why?
Power, money.
Because the money just leaves, right? like my kids would never turn off the lights. I'd be like, you get no allowance this week. There is a spigot attached to this house. It's called money, and it goes out. Right? Okay? So, all right. So what's another, I'm getting a little bit off topic here. What's another way to deal with this? I want you, don't use electricity. Go back to being a Luddite and hug trees. I want you to run an experiment tonight. Okay? Before you go to bed. Whether it's in your room or your house, like if you live in a house like a living room, but if you have just yourself in your room, turn off all the lights. Keep your eyes open, but turn off all the lights. And just look at how many little LED lights are telling you something. There might be one on your computer monitor. There might be one on your TV. There might be one on your Xbox. There's probably one on your modem. There's like it seems like every device now has to have a little blinky light on it, right? That tells you something. What's it telling you? Not so much on or off.
Oh, it's getting power.
Whether it's doing something or it's asleep, a television, like a flat panel 4K television, right? Depending on the size, when you hit the button to go off, doesn't go off. It turns the screen off. But what does that TV need to be ready to do? Turn back on it at instant. I must have it now. Right? While it's just sitting there, they can consume up to 15 watts of energy. Just sitting there, doing nothing.
Instead of getting a TV remote, get a smart thing that you can
turn off the power to your television. In fact, the only way, so this is called power vampires or vampiric power. It's devices that are off, but aren't really off. PlayStations, Xboxes are notorious for this. You turn them off. Normally gaming, they'll use about 400 or 500 watts. You turn them off, they're still consuming 100 watts. Yeah, they've gotten better over the years. I think the PlayStation 5 now in its sleep mode is about 10 watts. But it used to be like, especially the Comcast set-top boxes, the DVRs that were always recording things, you turned them off and their power consumption stayed the same. They were like 120 watts just all the time, on or off, right? Because you had to record DVR that, right? Okay, right? So in my house, right? Okay, this is Mr. Balogh's, right? All of my devices are connected to power strips. So I can walk up to the entertainment center and I hit a switch. It all gets disconnected, right? So there's no power vampires, right? I don't put my internet modem. I let that run 24/7, okay? But if it's a device that is not in use, it's dead. It's disconnected, right? So there's ways to think about this, and power vampires are kind of a big one. Okay, dad mode off. All right, teacher mode back on. So how do we calculate this thing, right? This is not rocket science. That comes later. We want to know the resistance, and we know the voltage and the current. How do we know it's voltage and current? Look at the units, right? There's your volts. What's 12 amps? It's the current. So how are you going to find the resistance? You're going to meditate on it. Ohm's law, right? 120 volts over 12 amps. What is that? 10. Okay. So that vacuum cleaner, right? Does it have resistors in it? Like actual circuit unit things called resistors? Probably not. Okay. But it has a lot of wiring in it. Okay. And it's got a motor and all that kind of stuff. And so it has this effective resistance, right? The vacuum cleaner needs 120 volts and it's running at 10 amps. If you look at the little labels on the sides of electrical things, it'll tell you power, voltage, current, right? It'll tell you these numbers by law so that you can figure out exactly what this device is doing, okay?
How much energy is it actually?
Okay, good. I'm glad you asked that question. How much power does it use?
1,440.
How'd you do that? Power is current times voltage, or current squared times resistance, or voltage squared divided by, you can do them all, they all get the same number, right? The current is 12 amps. The voltage is 120 volts. What was it, Brandon?
1440.
1440 watts. Watts. Got to be careful, right?
But some of that is being eaten up by resistance.
Well, but the vacuum cleaner draws 12 amps at 120 volts. So not all of that power is going to cleaning your carpet. Right? Some of it's going to heat and noise and a bunch of other things, right? I'm not talking about cleaning your carpet. I'm just talking about the electrical parts of the system, right? So how many kilowatts is this?
1.4.
Yeah, 1.44 kilowatts, right? And so if you run it for an hour, how much energy is that? 1.44 kilowatt hours. Times I think right now it's 18 cents in California for tier 1. But wait, there's more. Not only do you get charged for the actual, like, you know, per kilowatt hour up here, which they charged me $50 back in 2009, right? They charged me, of that 50, they charged 21 for generation, 4 for transmission, 15 for distribution.
What's the difference between transmission and distribution?
Yeah. What's the difference between transmission and distribution?
Like
Transmission is getting it from the dam to my house or from the nuclear power plant to my house, right? Distribution is sharing it with my neighbors. The town, the city, all that kind of stuff, right? Substations, all that kind of. Public purpose programs.
What is that?
I had to call up. I was like, I get what nuclear decommissioning is, right? And I'm like, 12 cents? Seriously? Can we up that to 50?
Yeah, right.
Right? Like, come on. Public purpose programs, $2.41. What the heck did I pay for?
Is that paying for the people that like have like, so the people that said like, oh, I need help and like I don't have enough money, so like.
It's a part of that. Do you know what the PG&E representative told me on the phone?
I don't know.
Oh, that goes in our pocket?
No. He said, do you know that little stuffed hat mascot that goes to the elementary schools and teaches kids about? I was like, are you kidding? Are you kidding me?
$2 for a mascot?
And but that was the first thing the PG&E representative told me.
Oh.
Did you know that there was a little stuffed? It looks like a safety hat.
I didn't know.
And it's got blue legs.
Well, I guess that's money going to education, I suppose.
I've never seen that.
I don't know.
Maybe after my call, they got rid of it because I was mad.
What's a DWR?
DWR bond charge. I don't know anymore. Department of Water Resources or something like that. Okay, and then the bond is a like a tax, right? Ongoing CTC. I don't know. Energy cost recovery amount. I'm not sure, but I think that one is. We didn't charge you enough, so let's just add something.
Sure.
Okay.
What's CTC?
I don't know. Okay? I can do quantum mechanics. Okay? But there are some things I don't understand. Right? It's the cost of doing business, apparently.
PG&E really does like to make their bills overspeed.
No, okay. Let's not just blame PG&E for this one. Let's put blame where blame is required, okay? Much of these things are legislated.
Yeah.
Okay?
U.S. government.
So write your congressperson, right? You're talking to somebody that's borderline socialist and is like, energy should be free for everybody. I don't understand what's going on, right? Water, power, internet, boom. Should just be available to everybody. We're in a nation that defines poverty as only having one car and one refrigerator, right? The fact that children in our country go hungry is shameful for the level of sophistication we live at, right? Sorry. I used to say I wasn't political. I am very political because I think we should argue and talk about these things, right? What I am is not partisan. I don't care whose idea it is. If it's backed up by data and it's a good idea, let's do it. Whether it's the Republicans or Democrats, I don't care. But political, I am very political. Let's figure out how to solve the problem. Anyway, sorry. So let's ask the question, how much does it cost to run a 100-watt light bulb? Right? I think this is the question somebody was asking, right? Like, how much does it cost, Mr. Balogh, right? And you can sub in any device. Your laptop, just look at its charger. See how many watt, like my laptop at home is a 250-watt power supply, right? That's only if it's doing like really big computations for games or something like that, right? Normally, I have a power meter I can plug in that shows me in real time what it takes, right? That kind of stuff. So, but don't get nerdy like me if you don't want to. 100-watt light bulb for 8 hours a day. What's the first thing we have to calculate?
Kilowatt.
Like the kilowatt hours, right? The amount of energy that it takes, okay? So a 100-watt light bulb is how many kilowatts? Divide by 1,000. 0.1 kilowatts. Okay? And then we do that for 8 hours. So what are we at? So we take the 100. I shouldn't have written an equal sign there. Okay? So it's 100 watts. It's 0.1 kilowatts times 8 hours. What does that give us? 0.8 kilowatt times hours, right? Per day, isn't it? Right? Because we're saying we're running it for 8 hours a day. And then 1 month, on average, yeah, I know. But on average, how many days are there in a month? 30, right? There's different value. But we'll just say 30-day month, right? Okay. So we do that for 30 days, right? Per month. This is basically a chapter 1 unit conversion problem, right? Once you get the kilowatt hours, you're doing chapter 1 stuff. Okay? Whatever 0.8 times 30 is, I've closed all my notes in my anger. What is it? $3 and...
Well, that's after you.
What's 8 times 3?
What's
24?
2024, and then you times it by 14 cents. Did I do that?
14 cents?
That's what it says. It's 14 cents per hour.
Oh, you guys are ahead of me. I want the interstitial number.
It's 24.
24. So it's is it 2.4 kilowatt hours in the month? Did we do that right?
No, I think it's 24.
Is it 24?
Yeah.
Because, zeros.
Yeah.
Okay, so there's 24 kilowatt hours in that 1 month thing that we did, right? And then we have this, did I say 14 cents per kilowatt hour?
Yes.
So if we did 24 kilowatt hours total, and it's 0.14 of a dollar per kilowatt hour, right? That's the cost thing. Those cancel. I end up with dollars, right? I got $3.36.
How many light bulbs are in the average house?
Right? Right? Now, hopefully, your house is not full of old-fashioned incandescent bulbs anymore. Like, we've actually done a pretty good job in America of kind of wiping those out. They were made illegal, and then when Trump was elected the first time, he brought them back.
Yes. And then Biden put down all.
LEDs are getting a lot better too. They don't have the flicker anymore.
Yeah, they don't last as long as they say on the box. Don't ever believe that it's like 30 years or whatever, because it's not. The LED itself is 30 years, but the circuitry connected to it can't last that long.
They don't last as long because we can design it that way.
Because heat is a problem.
Then you can make a more expensive light bulb last longer.
Yeah, but people don't want to buy it.
Yeah.
Right? So it's all about a race to the bottom. So that's how much it costs just to run that one light bulb. Do yourself a favor today. Go home, count the number of lights that are on in your house when you walk in. Especially if you live with other people. Right?
Keep out of your roommates.
Whatever. Okay? Tell them your physics teacher said so. Okay? We're going to get to electrical circuits, parallel resist, and series next time, but let's just finish up your house. These always look surprised to me. Right? Angry or surprised or shocked. Pun intended. With a little tear. Is there a teardrop coming out of one eye?
Oh, it is, yeah.
This one's bigger than this one?
Yeah, it's funny.
Why?
It got shot.
Polarized, okay? It's made so that you have to plug it in a certain direction, okay? Back in the old days, they weren't polarized. You could invert the plug, and instead of all the electricity going to the inside of the device, it could have gone to the outside shell of the device, okay?
And then the other ones are
Bad day. And then this is ground, okay? It's connection to the ground. Not all things need to be grounded, okay? So no panic there, right? By standards, okay, there is a neutral and a hot wire behind that plug. The hot one's supposed to be black. The neutral's supposed to be white. The ground is supposed to be green. But if you open up a box and you look in, sometimes there's blue. Or red. Or purple. And I want to strangle the electrician that installed it in my house. I'm just like, okay.
Well,
So,
red is technically permissible.
what?
Red is technically permissible.
They're all technically permissible. Okay, but they can be
That makes sense.
messed around. What?
I said red for hot.
Yeah, red is used for a three-way switch. Anyway,
Oh,
there's lots going on there. The problem is on the backside of an outlet, there are no fewer than 9 places to connect a wire. Electricians are some of my favorite people because I think they do magic, right? But even an electrician that's worked for years can still mess up when there's 9 places to connect wires, right? And you're not careful and you're not like concentrating while you do it, which is why like when I first bought my house, I grabbed a socket tester and I just plugged it into every socket in my house. And sure enough, 2 of them were wired backwards, right? Hot for neutral, okay? Which in the grand scheme of things isn't as bad as say hot to ground. That would be really bad, right? But like I found 2. And maybe it wasn't the electrician's fault. Maybe it was the former owner's fault, right? Doing some DIY or whatever, okay? But they were 2 that were not right, okay? And I fixed it. So yeah, there's a bunch going into that, right? Some of you may have seen this, or maybe there's a 4 outlet version. This is a 240 volt plug, usually for like a dryer or a stove or something that requires a lot more energy, like your AC unit might have something similar. Or AC is probably hardwired into it. But your house from the street gets 240 volts, usually about 100 amps. Okay? Some newer homes get 200 amps. But that's like the maximum. So when it gets to the panel on the side of your house, in that panel, they will split the 240. And what the 240 is it's positive 120 and negative 120. So if you hook across positive 120 and negative 120, what do you get?
0.
240 volt difference. Try it sometime. What's 120 minus a minus 120? 240. So that's what they'll do. And so they can power high power devices, but also they can then just split and take the positive 120 and make it your household circuit. Neutral supplied by PG&E. It's supposed to be the reference. So like, how does the 120 volt line know to be 120 volts? It's comparing to the neutral or reference voltage that's coming from PG&E. So PG&E doesn't have to make that 0. They can make the reference 100 volts. And then what would that mean? They may need to make the plus 120? 220, so that there's a 120 volt difference. In practice, power companies try to make the neutral as close to 0 as possible. That's just efficient, okay? But it doesn't always have to be that. What has to happen is they maintain the 120 volt difference between those things. So electrical devices know what to accept. Ground is connected literally to the ground next to your house. There's, if you have a gas line that runs in near your electrical panel, it's probably a wire that's just wired onto the pipe, the gas pipe that comes in. Other places, it'll come out of the box and there'll be like a metal rod that's been driven into the ground and they'll wire it up to that. Okay, so it's literally ground, like the dirt. Okay, because the ground is a great place to get that from. The reason you might want to have a grounded device, this drill, like an old-fashioned drill, if there's a short circuit on the inside and there's no ground wire connected to the device, you can become the path to ground for a short circuit. So electrocutions are more common on older devices, like old drills, old radios, old power tools, if you get the polarization wrong and there's no ground. Once you put a ground into the circuit, then the device has an easier path to ground. The current will go really high, but then the circuit breaker will go, oh, wait a second, something's wrong here, and it'll shut off the current. But at least you as the user are not in the electrical pathway. To get there, what is this a picture of? That's a neuron. Basically, everything I just said about electrical circuits can be applied to this. Because how do neurons work? Electrical impulses across cell membranes, sending electrical signals, right, along wires, right? And what we're going to do on Thursday is we're going to get into the series and parallel nature of the kinds of connections you can have. Not just in your house, but in your brain. And I'll see you then.
You can't have a red wire.